Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms, that is a greedy method. So in our previous sessions we have seen one methodology, that is divide and conquer, where we are going to divide the complete problem into different parts and recursively we are going to solve each and every problem, and after that integrating all the solutions will give the main solution. And for that we have seen different examples or applications, right? Now we'll say one more concept of this solving a problem, that is a greedy method. So this is one more methodology in order to solve the problem, right? And this greedy method is mainly used to solve the optimization problems, right? So it's mainly used to solve optimization problems. Now here the question is, what is meant by this optimization? So optimization, that means selecting the best solution among multiple alternatives. Okay, so we are having a lot of alternatives, so we need to select the best solution or the worst solution. So for every problem there might be having some constraint or may not be having the constraint. So based upon that constraint we need to select one option from the alternates. So that such type of problems we call it as an optimization. So optimization problem means it's a problem which can have multiple alternates. So usually these multiple solutions will be considered in a subset. Okay, that means a set of solutions. So the procedure or a process which gives a solution or the procedure which gives the better result is known as feasible solution. Feasible solution, right? So a normal solution, whether it may be best or worst or a minimal or a maximum, whatever it may be, the solution for a problem is called as a feasible solution. And the collection of all these feasible solutions will be in a subset. Okay, so there will be a set of feasible solutions. And from these feasible solutions, based upon the constraint, so we can select one solution, and that will be the optimal solution, or we can call it as a best solution. So the best solution among set of feasible solutions is known as optimal solution. Okay, so don't get confused among these two, optimal solution and feasible solution. So any solution can be considered as a feasible solution, and based upon the constraint, selecting one best solution among these feasible solutions is called as an optimal solution. So that's why we call it as an optimization problem. So we need to select the best solution from these feasible solutions, right? So let us take an example, simple example that you can understand, right? So here the real world problem is traveling from city A to city B. Okay, so there is one road, so through streets, okay, through the streets, and there is a one more way, which is a bypass. Okay, so there are two solutions. So we can travel from city A to city B among these two paths. Okay, so the feasible solution is through streets and through bypass. So here you can see feasible solutions are, one is a bypass, so using the bypass, and another one is by using streets. For example, if we use a bypass, let us consider some 15 kilometers, and if you use streets, let us assume that 10 kilometers, the distance, okay, 10 kilometers. Now, which path we need to select? So here, constraint. Consider a constraint. Okay, based upon the constraints, we are going to select either bypass or a street. So, if you use a bypass, less traffic will be there. Less traffic. And if you use it streets, obviously there will be a traffic, and also there will be some signals, traffic signals. So if you use a bypass, it may take a less than 1 hour time, and if you use the traffic signals, it may or may not take, so it may take greater than or equal to 1 hour. So if you want to reach the destination within a short period, within a short time, so without any traffic, you can select this one. And if you had any work in between the city, in between the streets, then you need to use this streets. So that means we are having multiple solutions, okay, multiple alternatives. So based upon the constraints. So if you had some work, okay, if you had some work in between city, so we need to go through streets. If you are not having any work, and if you want to reach quickly without, avoiding the traffic signals, we can choose this bypass. So this type of problems, we can call it as an optimization problem, and these optimization problems can be solved by using this greedy method, right? So hope you understood the procedure. Now, what are the applications? That means where we are going to use these greedy methods. Few applications, okay? So few applications. Few applications where we are going to use this greedy method. The first one is a selection sort. So in order to arrange the elements in a sorted order using the selection sort mechanism, we'll use this greedy method. And just now we have seen finding shortest path. Finding shortest path. For example, consider a graph. So we are having, so A and B, some 5 and 10 and 6 and 5 and 7. Now, see, if you want to reach from A to C, you can see you can reach C through B. So total cost will be 15. So A to C via B, it is 16. A to C directly 6, and A to C via D, it will be 12. So which one will be the shortest? So 6 will be the shortest. So in all these three cases, we can reach the destination, but the constraint is minimum shortest path. Okay, so finding the shortest path with a minimum distance. And such type of problems, we are going to use this greedy method. And then fractional knapsack problem, job sequencing, okay, so finding minimal spanning tree, so there are two approaches by using a Kruskal's or Prim's algorithm, so minimum spanning tree. So all these are the few applications where we are going to use this greedy method. So in our further sessions we will see one by one, so how we can apply the greedy method and how we can find the solution for all these applications, right? So let me explain you about one example and I will wind up about this introduction of greedy method, right? So example, for understanding I'll give the example. So I am taking one example which you frequently listen. So that means I am having some 25 rupees, okay, 25 rupees, and I need a change, okay, need change with minimum number of coins, so coins available, so 5 rupees, 2 rupees and 1 rupee. So there are 3 possible coins. So we need to get a change for 25 rupees with the minimum number of coins. So the solution 1 is, see, 5 into 5 rupees. Okay, that means it requires 5 coins. Solution 2, we can take 4 into 5 plus 4 5 is 20, 2 into 2 rupees plus 1 into 1 rupee. So how many coins it requires? 4 plus 2, 6 plus 1. So it requires total 7 coins. And simply we can say solution 3, so 25 into 1 rupee, which requires 25 coins. Similarly, solution 4, we can have 2 into 5 rupees, 10, and 10 into 2 rupees, 5 into 2 rupees, so 10, 20, 10 plus 10, 20, and 5 into 1 rupee. So total how many coins? 2 plus 5 plus 1, 5, 12 coins. So there are a lot of possibilities, So using 5 coins we can get a change for 25 rupees. Using 4 5 rupees coins and 2 2 rupees coins and 1 1 rupee coin, still we can get the 25 rupee change for 25 rupees, but it requires 7 coins. And still we can get a 25 1 rupee coins. So to get a 25, so it requires 25 coins. And here, in order to get the 25, we can have a 2 5 rupees coins, 5 2 rupees coins and 5 1 rupees coins. So obviously we can get the 25, change for 25 with the 12 coins. So that will be keep on moving. These are all the feasible solutions. In all these cases we are getting the solution, right? But what is the constraint here? Minimum number of coins. This is the constraint. Okay. So this one will be the constraint. So we have to satisfy this constraint. So based upon that constraint, we can select this optimal solution among all the feasible solutions. Among all the feasible solutions, we can select the optimal solution. So this is the procedure of finding the solution for optimization problem. Okay, this procedure we call it as a greedy method. So based upon the constraint, getting the best solution or optimal solution. Okay, so if there is no constraint, so anything can be accepted. We can accept anything. Either it may be the best solution or the worst solution. Whatever it may be, we can accept anything if there is no constraint for a problem. If there is a constraint for a problem, obviously from the multiple alternatives we have to select the best solution which satisfies the given constraint. Right? So let's stop here. Hope you understood the introduction to this greedy method. So let us move on with the next concepts of applications, explaining the applications using this greedy method from the further sessions. Right? So if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So today we will discuss about an application of a greedy method. So that is job sequencing with deadlines. So we have seen the introductory part of greedy method, so which is mainly used to solve the optimization problems. So optimization problem means having more than one solution and selecting the solution based upon the constraint. So that is called as a greedy method, and one application of applying this greedy method is job sequencing with deadlines. So first let us understand the problem and then we'll move on with the solution, the procedure, how we can solve the problem. So the problem is job sequencing with deadlines. So here you can understand with the name, that is a job sequencing with deadlines. So here we'll be having the first one, jobs, the number of jobs. So we can consider them as a process, number of processes we need to execute. And second one is a profit. So profit means, so which we can profit after completion of the each and every job. Okay, so or we can say it as a cost. Okay, the cost. And the third one is deadline. So the name itself indicates for every process or for every job there will be a deadline. So that particular job should be completed within that particular deadline. Okay, so these three are most important in this job sequencing problem. So we need to complete the processes or jobs within the given deadline with a maximum of profit. Okay, so that is our problem. That is our problem. And here we need to remember a few points, most important points. See, so before going for the solution for this job sequencing, the first point we need to remember is only one processor. We are going to execute on only one processor. So one processor will have to execute all the jobs. Okay, then no preemption. So if you are aware about the scheduling algorithms, you might be knowing about this preemption and non-preemption. So preemption means, so if there is any job with the highest priority, then the executed process will be put on hold and the CPU will be given to the highest priority processor. So that will not be done in this job sequencing. That means once the job is assigned to the processor, it have to complete, and that means the remaining jobs have to wait until the job gets completed by the processor. So no preemption. So once a job is given to the processor, so we have to wait until it completes its execution. So no preemption. Okay, so mainly these things, and one more, sorry. So every job takes 1 unit of time, 1 unit of time to complete. Okay, 1 unit for completion. So every job takes only 1 unit for completion. Okay, so don't get confused about this deadline and this 1 unit. So deadline means the complete time, so upon which the job has to be get completed. Okay, so but every job takes only 1 unit. Now see, these three things are the most important, and we have to remember before applying the job sequence. In one processor, no preemption, and every job takes 1 unit for completion. Right? Yes. Now we'll see the procedure, or we can call it as an algorithm. So the first step, let us take an example, then we'll move on with the algorithm. So first we'll go with the example so that you will be understanding perfectly. Example. So let us take a number of jobs. Let us consider 5 jobs: J2, J3, J4 and J5. So these are jobs. And the second point is a profit. How much profit we'll get after completion of that particular job. Let us take this as 15, 10, 20, 25 and 5. This is a profit. Okay, this is a profit. And the third one is the most important, that is a deadline. Okay, so deadline. Let us take 2, 1, 3, 2. Okay, let us say randomly I have taken this one, right? So this is a deadline. So we have assumed that only one processor, no preemption, and the last point is every job will take 1 unit for its completion. So let us assume that this is a 2 units, this is a 1 unit, 3 units, 3 units and 2 units. Now what is an algorithm? So what is the process we have to do? So first we have to find out the maximum deadline. So what is the maximum deadline here? So in order to avoid the confusion, let us take it as 3 and let us take it at 1. Okay, right, maximum deadline among all the deadlines. What is the maximum? So the maximum is 3, so 3. Now we have to draw the Gantt chart. Gantt chart means we need to draw this one. See, so this is a Gantt chart: 0, 1, 2 and 3. See, this is 1, this is 1, 2 and 3. So 3 units. You can assume that this is a 3 units, and we need to complete the jobs with the highest, more priority, with more number of priority, right? Now what do we have to do? The next one, sort all the jobs in a descending order with respect to the profit. So sort in descending with respect to profit. Here on the right. Okay, profit. Now rearrange the jobs based upon the deadlines. First, what is the highest? 25. So J4 will be the first with the 25, and the deadline is 3. What's the next one? 20. So J3 21. So J3 21. Next 15. J1 15 2. J1 15 2. Next J2 10 1. J2 10 1. next J5, 5 and 2. So we have arranged the complete jobs in a descending order with respect to the profits. See, for example, let us consider this was not done. Okay, this was not done. So in an order, complete the jobs. So J1 should be completed within a 2 deadline. So let us take here J1 with a profit 15 and J2 with a 1 block, but it doesn't happen here because during the first unit J1 will be completed. So J3 it was also not completed. Next we can go with the J4 with a 25 profit and J5 with a 5 profit. So you can complete the J1, J4, J5, the 3 processes with a profit. So 15 plus 25 plus 5, so which is nothing but 45. Okay, and also we can complete, see, we can complete J1, next J4, okay, sorry, already we have done. So we can complete here J2, J3 and J4, right? So first J2 will be taken here, J3 we can complete, J4 we can complete, and the profit will be 10 plus 20 plus 25. Okay, so here we will be having a lot of solutions and we can't say that this will be the optimal solution. Okay, so there will be a lot of solutions. So we can execute J1, J4, J5, we can execute J2, J3 and J1, we can execute J2, J3, J5, etc, etc, right? So what happens here? So we need to select the optimal solution based upon the constraint. So here what is the constraint? We need to get the maximum profit. Now in order to find out that maximum profit, we are going to see this process, sort in a descending with respect to the profit. So this we have done. Now what we are doing? So first J4, the first process with the highest profit. So the constraint is a profit, highest profit. So based upon the profit, we are arranging the jobs in a descending order. So what is the maximum deadline limit? 3. So we can assign J4 in the last one. J4 with a 25. Okay, hope you understood. So the maximum deadline to complete the job 4 is 3. So we are going to select the third one, that means the last option, okay, in the third unit. So the profit will be 25. So this completed. Next, J3 with the highest priority. So because this is a descending order, so 20 is the next priority, and this J3 should be completed with a 1 unit. Okay, deadline is 1. So we can't assign J3 here because after 1 we can't assign it because 1 is the deadline. So J3 will be assigned here. J3 will be assigned here with a 20 profit. Next, J1, 15. That's the third highest profit. And what we are doing? That's just 2 is a deadline. So here we can assign the J1. So what is the highest profit? 15. So 15 is the profit. Now the overall profit of completing the 3 jobs, J3, J1, J4, what is the profit here? So 20 plus 15 plus 25. So what happens here? So 35 and it will be 60. So 60 is the highest profit in order to complete the jobs. Okay, so this is how we have to solve the job sequencing using the greedy method. So greedy method means we'll get the alternate solutions, and from that alternate solution based upon the constraint we are going to select the best or optimal solution. So here also we can execute J1, J2, J3 or J2, J3, J5 in these 3 slots, or J2, J4 and J5, or J2, J1 and J4. So there will be a lot of options. Okay, we can complete. So let us take J2, J4, J5. So this is one solution. Okay, executing all these, completing all these 3 jobs with a particular profit. What is the profit here? J2 10, J4 25, so 35, and it's a 40. And also you can go with the J2, J1 and J4, J2 10, 15, 25 and 25. It will be 50. So in both the cases we will get the profit, but the constraint is getting the best solution or optimal solution based upon the constraint. Constraint is the highest cost, okay, with a high cost. So for that we have done, so the highest profit, high profit is 60 by executing J3, J1 and J4, 3 jobs. Okay, so this is how we can solve the job sequencing with deadlines problem. Okay, now we'll go with the algorithm. Hope you understood this one. So take a few more jobs. Let us take some 10 jobs and try to solve the problem so that you will be understanding more, right? So now I will write the algorithm and I will wind up. Okay, so algorithm. So step 1. What is step 1? We need to find out the maximum deadline. Find maximum deadline. And step 2. What is the step 2? So after finding the maximum deadline, we need to draw the Gantt chart. Draw Gantt chart with maximum deadline. Maximum deadline. So we have drawn. And step 3, after completion of this Gantt chart, we need to sort the jobs according to profits. Sort all jobs with respect to profits. Step 4. What we have to do? So we have to find out the appropriate slot to fix the job. Search empty slot to fix job. To fix job. Okay. So we having or in a deadline near to its maximum. Near to its maximum. So this is the process we are going to do, right, for solving the job sequencing with deadlines. So here the time complexity for this one, time complexity. So first we are going to sort out this one. Okay, only 2 steps. So sorting all the jobs with respect to the profits, which will give the order of n log n. So we can apply any sorting mechanism, quick sort or bubble sort, anything. So I'll go with the quick sort, okay, because we have seen in our previous sessions by using the divide and conquer. So it will be order of n log n plus what we are doing, searching the empty slot to fix the job in a deadline near to its maximum. Near to its deadline, okay, right? So how many searches we have to do? So if there are n jobs, we have to search for n slots, okay. So obviously it will be order of n square. So n jobs, n slots. Okay, m jobs and n slots, or n jobs and n slots, whatever it may be, no problem. So it will be order of n square. Order of n square. So the highest degree, what is the highest degree? This one. So the time complexity. The time complexity is order of n square. Order of n square for this job sequencing with deadlines, and we have followed the greedy method. Greedy method. So that means finding or getting the feasible solutions, and from that feasible solutions we are selecting the optimal or best solution, right? So let's stop here. Hope you understood this one, and if you are having any doubts regarding this job sequencing using the greedy method, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So in today's session we'll see one algorithm to find the minimum cost spanning tree, that is a Kruskal's algorithm. So in the previous sessions we have seen one algorithm to find the minimum cost spanning tree, that is a Prim's algorithm. So before going to that, let me revise the previous concepts, that is what is a spanning tree. So consider a graph, and a spanning tree is a subgraph derived from that particular graph, so with n vertices and n minus 1 edges, right? And minimum cost spanning tree means the spanning tree with a minimum cost. Okay, every edge will be having a cost, so having a minimum cost to construct the tree is called a minimum cost spanning tree. So in order to find out this minimum cost spanning tree, there are two approaches as we have discussed earlier, that is a Prim's algorithm and Kruskal's algorithm. So in the previous sessions we have seen the Prim's algorithm, now we will see the Kruskal's algorithm. So here the step 1, the first step means here arrange all the edges in ascending order. Based on cost. So every edge will be having their own cost, so we need to first arrange all the edges in ascending order based upon the cost, right? Ascending order means lower value to the higher value. So we need to find the minimum cost spanning tree, so that's why we are using this ascending order. And then step 2, consider least cost weighted edge and include in the tree. Include it in tree. So consider one by one and just include that in a tree. And if the edge forms a cycle, just ignore and consider next least cost weighted edge. So every time we will consider an edge and we have to include that on a tree. So if by adding that edge, if it forms any cycle, so just we have to ignore that edge and consider the next least cost weighted edge, because a tree should not have the cycles. right? So graph can have the cycles, but the tree should not have the cycles. So here we are using this Kruskal's algorithm to find the minimum cost spanning tree, right? And the third step, repeat step 2 until all the vertices are included in a tree. So we know the spanning tree, right? So if the graph is having some n vertices, then the spanning tree should have the n vertices with n minus 1 edges, right? So similarly, we have to repeat the step 2 until all the vertices are included in a tree. So by following these steps, we can find the minimum cost spanning tree by using this Kruskal's algorithm, right? So hope you understood this one, and now we'll see an example and we'll find the minimum cost spanning tree. So let us consider this example, and this is a graph and we need to find the minimum cost spanning tree. So what is the first step? We have to arrange all the edges in an ascending order based upon their cost. So here the least cost among these things are 2. So first let me write all the edges with a 2. So here you can see A to B. A to B is a 2 with a cost 2. So this is a bidirectional, because this is a bidirectional. We can simply consider A to B or B to A. Next, there is one more thing, that is a 2, D to E. Again it is a 2. Next, 3. So we are having A to C. A to C with a 3. And one more, B to D. B to D with the cost 3. And D to F. D to F with the cost 3. Then what about next one? It's a 4. So 4, B to E. B to E with a 4. And C to E with a 4. Next one is a 5. So B to C, 5, and E to F is 5. So you can observe these are the edges arranged in an ascending order, because you can observe the cost, so from lower to higher. Now what is the first step? Consider each and every least costed edge and include it in tree. So first consider A to B. So I will construct the tree here. So A, B with a cost 2. Next, D to E. So D to E. So D to E. So here it is a D. E. So what is this one? D to E, again 2. Next, A to C, 3. A to C, there is no C, so we have to add it. A to C, 3. Next, B to D. B to D. So it doesn't form a cycle, right? B to D. So just include that one. B to D, again it is 3. Next, D to F. So there is no cycle, so I will construct here F. D to F, it is 3. Right? Next, B to E. So if you give the edge here, B to E, it forms a cycle, right? It forms a cycle. So we should not consider this one. So this should be rejected. C to E. C to E. Again, if you form an edge, if you give an edge, again it forms a cycle, right? A, B, D, E, C, A. So we have to reject that. B to C. B to C. Again, if you form an edge, so it forms a cycle. So we have to reject. E to F. E to F. If you consider the edge here, again it forms a cycle. So you have to reject. So you can see in our graph there are 6 vertices. 6 vertices, and our spanning tree consists of 6 vertices. 6 vertices. Right? And here the edges 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. So 3, 6, 7, 8, 9 edges. So there are 9 edges. you can observe here 1, 2, 3, 4 and 5. So 5 edges, which is nothing but vertices minus 1, right? If there are n vertices, there should be n minus 1 edges. So it satisfies. Now you can observe all the vertices are covered, so we can consider this as a minimum cost spanning tree, which can be represented as MST, minimum cost spanning tree. So now what is the cost here? Consider cost here. So cost of this one will be 3 plus 2 plus 3 plus 3 plus 2. So the cost will be 5, 8, 11 and 13. So cost is 13. So the minimum cost we can create or construct the spanning tree is with 13. So you just remember this is the same example we have taken in the Prim's algorithm also. So there also we have constructed the minimum cost spanning tree with a cost of 13. So once just observe the session, so I will post the link in the description, so you can follow that one. So that is the procedure of Prim's, and this is the procedure we need to follow for the Kruskal's. So this procedure is Kruskal's algorithm, right? So first we have to arrange all the edges in an ascending order based upon their cost, and then consider each and every edge and construct a tree. And if by adding the edge to the tree, if it forms a cycle, just ignore that and consider the next least cost edge, right? So we have to repeat that one until all the vertices are covered. So here there are 6 vertices, all the 6 vertices have been covered with a cost of 13, right? So hope you understood this one. So this is a Kruskal's algorithm to find the minimum cost spanning tree, right? So if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. So first let us see what is this spanning tree, and then we'll go with the construction of this spanning tree. So a spanning tree is a subgraph. So we all know about the graphs. So graphs are nothing but connected nodes with the edges with the cycles, right? So it is, the spanning tree is a subgraph of a graph with the vertices and edges. So a graph will be having the vertices and edges with the cycles, right? But here the tree means it's a subgraph with no cycles. With no cycles. So here if it is not having any cycles, we call it as a tree, right? Now, so we need to follow a few points or a few rules while constructing this spanning tree. The first one is, so the spanning tree should connect all vertices of a graph, right? So it should contain all the vertices which are available in the graph in the spanning tree. And the second one, if graph is having n vertices, then the spanning tree should have n minus 1 edges, right? So n vertices in the graph, then spanning tree will be having n minus 1 edges. And the third one should not contain any cycles. So we need to follow these rules while constructing the spanning tree, right? So let us take one example, so graph, and we'll see how to construct the spanning trees. So first we'll consider the graph, and then we'll construct the spanning trees from that particular graph. See, so we have to follow all the rules, right? So let us take an example with the 4 nodes. So A, B, C and D. So these are the 4 nodes, and this is a connection between all these nodes. So this is a graph. Okay, so edges, vertices and cycles, right? So now we should construct the spanning tree. So what is the first rule? First rule is number of vertices should be equal. Number of vertices must be equal in both the graph and spanning tree. So we have to connect all the edges. We need to connect all the edges. So I am writing all the edges here. Next, so these, if there are 4 vertices, we should connect with 4 minus 1 edges. So I will connect this one. So A to B, A to C and C to D. So this is a construction, right? So you can observe here, here we are having a 4 vertices and the edges are 4 minus 1, that is 3 edges. So this is one spanning tree. And another case, let us see A, B, C, D. So let us consider this one. So this is also a possible spanning tree from this particular graph, right? So because all the edges, all the vertices has been connected and the number of edges are n minus 1, that is 4 minus 1, and there is no cycle, right? And one more possibility. So this is one more possibility, right? So here also all the 4 vertices has been connected with n minus 1 edges, and there is one more possibility here. So this is one more possibility. Here also all the 4 edges, 4 vertices has been connected with 3 edges, because we are having 4 vertices, so the number of edges must be 4 minus 1. So this is the cyclic graph, and this is a acyclic graph. Acyclic graph is nothing but our trees, right? So all these are the spanning trees. Okay, all these are the spanning trees, right? So one graph can have a multiple spanning trees. So here we can have the 4 possibilities, right? And if you consider one more example, like a triangle shape. So this is a graph. So we are having 3 vertices and 3 edges, so that it's a graph. So this can be constructed as, so A to B, B to C, A to C, C to D, right? And A to B and C. So these are all the different possibilities of spanning trees can be constructed from this particular graph, right? So hope you got an idea about this spanning tree. What exactly this spanning tree? Spanning tree is a subgraph from the original graph. So with n vertices and n minus 1 edges, right? So we need to follow the 3 points. One is all the vertices should be connected, and if n vertices are there, n minus 1 edges should be there, and there should be no cycles. So this is all about our spanning tree. Now, what is the minimum spanning tree? Now let us see the concept of minimum spanning tree. So minimum cost spanning tree. So it is called as a minimum cost spanning tree. So let us consider the graph A, B, C and this one. This is a graph, right? This is a graph. So each edge will be having a cost. Each edge will be having a cost. We can also call it as a weight for the particular edge. Let us take here some 5, some 2, some 3. So the cost of an edge A to B is 5. The cost of an edge from B to C is 3. The cost of an edge from A to C is 2. Now construct the possible spanning trees. So the possible spanning trees are A to B, B to C, A to B, A to C, A to C, C to D. So these are all the possible spanning trees, right? All the possible spanning trees. Give the edges here. So 5 and 2, sorry 3, and here 5 and 2, 3 and 2. So now you have to, so you can observe here all the vertices has been connected. Okay, all the vertices has been connected, and here also all the vertices has been connected, and here also all the vertices has been connected, right? So here you can see there is an edge A to B, B to C. There should not be a cycle, right? So here it is A to B, B to C. So if you add one edge from C to A, so what happens? The starting vertices and the end vertices same. That means it forms a cycle. So we should not connect this one. So that's why we are not connecting, and this is a spanning tree, right? Now cost for this spanning tree is 5 plus 3, 8, because there are two edges with a weight 5 and 3. The cost of this particular spanning tree is 8, and the cost for this one is 7, 5 plus 2. So the cost for this one is 3 plus 2, it's a 5. So you can observe here for every spanning tree we are finding the cost. So here the cost is 8, cost is 7, cost is 5. Now we need to select the minimum cost spanning tree. So we will select the minimum cost spanning tree. That means the tree with a minimum cost of edges, right? So minimum weighted edges. So here there are two approaches to find the minimum cost spanning tree from a graph. So that is, one is a Prim's algorithm, another one is a Kruskal's algorithm. So in today's session we'll discuss about the Prim's algorithm. So before applying the Prim's algorithm on the graph, make sure that the graph should be weighted, connected and undirected. So unless the graph is weighted, connected or undirected, so we can't apply the Prim's algorithm. So make sure the first point before applying the Prim's algorithm. So the graph should be weighted, connected and undirected. And coming to the steps. So first we need to consider any vertex, because so we know the spanning tree definition. Spanning tree is a subgraph from the graph without any cycles, consisting of all the vertices of a graph, right? So consider any vertex of the graph. And the second step, find all the edges from the selected vertex to all the new vertices. So find all the edges. So among all the edges, you need to select the least weighted edge. So among all the edges, we need to find the least weighted edge and include it in a tree. So we need to construct a tree for that selected vertex and given the least weighted edge. And if the least weighted edge forms a cycle, so if you include this least weighted edge into a tree and if it forms a cycle, then simply discard. So if it forms a cycle, then simply discard that one and consider the next least weighted edge. So once you find the least weighted edge, you have to include it in a tree. So after including it in a tree, if it forms a cycle, simply discard that one and consider the next least weighted edge and include it in tree. And the third step, repeat the same step 2 until all the vertices are included in a tree. So once all the vertices are included, automatically that will be the minimum cost spanning tree, right? So this is how we need to find the minimum cost spanning tree with a Prim's algorithm. So here now we'll see an example and we'll find the minimum cost spanning tree by following all these rules. So let us take an example. So consider one graph. So consider this graph. So let us take some weights. So let us take these weights. Okay, this is a graph. Consider this graph. And we need to find the minimum cost spanning tree for this particular graph. So what we have to do, first consider any vertex, So I will consider A. I will start with A. So this is a A. So I have included this one in the spanning tree. Now consider all the edges from A. So you can see A to B with a cost of 2 and A to C with a cost of 3. right? A to B with cost 2, A to C with cost 3. So we need to select the least weighted edge because A is having two edges. One is from A to B, one is A to C, A to B, A to C. So consider the least weight. So this is the least among these two. So we need to add this B to the spanning tree. Now the spanning tree will be A followed by B. So with a cost 2. So this is the tree. This is the tree. Now what is the new vertex here? B. So what is the remaining vertex? Consider this one, A to C with 3, and consider the edges from B, right? So from B there is a vertex from B to A which is already covered, right? Because this is a undirected. Okay, this is a undirected. So B to A is covered. So we need to consider B to C and B to D. So B to C with a cost of 5 and B to D with a cost of 3, right? B to A, B to C, B to D, right? Now what happens among this one? We are having a two edges with a minimum cost 3, so you can select any edge, no problem. So I will select this one, B to D. I will select this one, B to D. Now the tree will be A, the tree will be A followed by B, B to D. So the edges are 2, 3. Now the spanning tree becomes this one. So in the first step, the spanning tree is this one. That means only one vertex. In the second step, so first step, second step, and this one is the third step. Now consider the remaining edges. What are the remaining edges? A to C with a cost of 3. B to C with a cost of 5, right? Now D is added here. Now consider the edges of D. So you can see D to B, which is already done because of undirected, right? So you can simply use this one, bidirectional, right? Right. So B to D is completed. Now D to E. So D to E with a cost of 2. And D to F with a cost of 3, right? So the edges of D are D to B, D to E, and D to F. So among the D to B is completed, right? Now among these, what is the minimum cost? So this one, least edge, least weighted edge. So consider this one. Now the spanning tree will be A, edge to B, edge to D, and from D to E. So the cost is 2, 3 and 2. Cost is 2, 3 and 2, right? And next, what are the remaining edges? Simply write here, A to C with a cost of 3, B to C with a cost of 5, and D to F with a cost of 2. Now E is added. So what are the edges of E? E to D, E to C, E to F. So E to D is completed now. Just discard that one. E to C. So E to C is not there. So we can write the edge E to C with a cost of 4. And E to F with a cost of 5. E to F with a cost of 5. E to F, right? Now among this one is the least weighted edge. Least weighted edge. D to F. So see, our graph, our tree will be A, B, D, E and F, right? So this is 2, weight 3, this is again 2, now again it's a 2, again it's a 2, right? You can observe here whether all the vertices have been covered or not. A, B, D. So there is no C is not there, right? So you can continue the process. So what are the remaining edges? A to C with a cost 3, B to C with a cost 5, E to C, D to F is completed. So E to C with a 4, E to F with a 5, right? Next, F, we have reached to F. So the new vertex is F. So write down the vertices of F. So F to D, F to E, right? F to E is completed. So F to D with a cost of 3. Now you can see among all these things, what is the minimum? A to C or F to D, right? F to D is also completed, right? F to D is also completed, so you need not go with this one. And one more thing is F to E. So that's also completed. F to E, we have written F to E here, right? So now among all these things, what is the minimum cost? A to C. So consider A to C and observe whether it is giving the cycle or not. It forms a cycle or not. So if you apply A to C, it doesn't form a cycle. So consider this one. So A to B, D, F, E, C. Right? Now you can give the weightage 2, 3, 2, 2 and 3. So you can observe here A to B with 2, B to D with 3, D to F with 3, D to F with 3. So D to F 3, okay, D to F is with 3. So this is D to F with 3 and then D to E is 2 and A to C is 3. So you can observe here all the vertices have been constructed, that means included in the tree. So A, B, C, D, E, F. So here we are having total 6 vertices. 6 vertices. So all the 6 vertices have been included. And now you can observe here the remaining edges. What are the remaining edges? So consider B to C with a 5 and E to C with 4 and E to F with a 5. So if you consider B to C, so if you add a B to C, it forms a cycle. So we have to discard this one, right? E to C 4, E to C. If you just connect this edge, again there is a cycle. So A, B, D, E, C, A. So again you need to discard this edge. And E to F, again if you connect this edge E to F, again a cycle forms. So again we need to discard these edges. So we have to discard these edges so that we can have this one. Okay. So hope you got this one. So I think these things are not clear. So I'll write the edges here. E to C with a 4 and E to F with a 5, right? So I think now it's clear. So we have to apply, we have to consider from the single vertex. You can consider any vertex and consider the edges, all the edges from that vertex to new vertices, and consider the least weighted edge. Okay, and continue the process until all the vertices will be connected. So this is the spanning tree, minimum cost spanning tree, for the given graph. What is the cost here? So you can observe the cost. I will write here. Cost is equal to, so what is the cost? 3 plus 2 plus 3 plus 3 plus 2. 3, 2, 3, 3, 2. So what is the total cost here? You can observe. So 5, 8, 10, 13. So 13 is the minimum cost for this particular tree. So the cost is 13. The cost is 13 to construct this particular spanning tree. So this is the procedure we need to follow for Prim's algorithm. Okay. So consider a graph and finally we are getting the minimum cost spanning tree. So we'll get many spanning trees from this graph. So as we discussed in the previous session, right? So we can get a many spanning trees from this graph, but we need to find out the minimum cost spanning tree. So this is the minimum cost spanning tree obtained from this particular graph. So let us consider this graph, and now we are supposed to find out the minimum cost spanning tree for this particular graph. So just recalling the steps, the first step we can consider any vertex, and the second step we need to find out all the outgoing edges from that vertex to new vertices, and consider the least weighted edge and include it on a tree. And after including the least cost weighted edge on the tree, if it forms a cycle, so we have to discard and we need to go for the next least weighted edge, right? And we need to repeat the same thing until all the vertices are included in a tree. So let's start with this one. So this is a Prim's algorithm. So by using this Prim's algorithm, we are going to find out the minimum cost spanning tree. So first we need to consider any edge, right? So the first step I will go with here. So consider A. Now what are the edges from this A? So edges are like A to D with a 5, and A to F with a 7, and A to B with a 14, and A to C with a 21. So you can see from A we are having a 4 edges: A to B, A to D, A to F, A to B, and A to C. Now the next step, we need to select the minimum cost edge, right? Least weighted edge. So among these, this is the least cost edge, right? So consider this one. So our next one will be A to D. A to D with a cost of 5. A to D with a cost of 5. Now, what are the remaining edges? Simply write down all the edges. So one is A to F with a 7, and A to B with a 14, and A to C with a 21. Now, consider the edges from D, right? Because the new vertex included in our tree, D. So write down the edges from D. So two edges are there. D to A already done. So D to F with 13, D to F with 13, and D to E with 22. D to E with 22, right? So among all these edges, so this is the first step. So among all these edges, what is the minimum cost? So 7, 14, 21, 13, 22. So this is the minimum cost. So consider this one. Okay, consider this one. Right? Now, the graph, the tree becomes A to D with a cost of 5, and from A to F, so the next cost is A to F. So A to F with a cost of 7. So what are the remaining edges? See, after this one, what are the remaining edges? You simply go with this one. So A to B with a 14. Next, A to C with a 21. A to F. So this already happens, right? Sorry, D to F. Okay, D to F. So D to F with a 13, and D to E with a 22. So now we are having one more vertex, that is F. So now consider the edges of F. So from F we are having how many edges? So 1, 2, 3, 4 and 5. So among all these things, F to A we have completed. So F to D or D to F. This is a bi-connected, so F to D or D to F both are equal. You can simply leave. F to E with a cost of 15. F to G with a cost of 18. F to B with a cost of 2. So these are the edges from F. So among all these things, consider the least cost weighted edge. So among these, this is the least cost weighted edge, right? Now the tree will be A, D, F, B, right? So this is 5 and this is 7 and this is 2. Now our tree is like this, okay, tree is like this. Now the new vertex added here, and consider all the remaining edges, okay, consider all the remaining edges. So what are the remaining edges here? So all these are the remaining edges. A to B with a 14, next A to C with a 21, and D to F with a 13, and D to E with a 22, F to E with a 15, next F to G with 18, F to B with 2. So our tree consists of a new vertex B. Now consider all the edges from B. So from B we are having only two edges, B to C and B to G and B to C, B to G, B to F and B to A. Now B to A, so there is already covered. B to F already covered, right? So we should not consider this one because we have already done, right? So this is already done, so we should not consider. So B to F, there is no edge. So B to G, 19. So B to G with 19 and B to C with 15. B to C with 15. Consider the least. Consider the least among all these things. What is the least one? So this one is the least. D to F is 13. So D to F is 13. So if you consider D to F, so it forms a cycle. You can observe here. It forms a cycle. So we should discard this D to F. We should discard this D to F because if you add this one, we'll get a cycle. So we should not consider this one. Next least. So there are two edges which are having the next least costed edge. So F to E or B to C. In such cases, you can consider any edge. Okay, here we are having two edges with the minimum cost. You can consider any edge. Okay, so I will consider B to C. I will consider B to C. Now the tree will be like this: A, D, F, B. Okay, so this is 5, this is 7 and this is 2. Now we need to consider B to C. What's the B to C here? Yes, B to C with 15. B to C with 15. Now consider all the remaining edges here. So A of B with a 14, right? So you can observe here. Okay, let us write down. No problem. Next, A to C with a 21, D to E with a 22, and F to E with a 15. Next, F to G with a 18, and B to G with a 19. Because we should not consider this one because we have already done the edge from B to C. Now there is a new vertex here included in the tree. Now consider the edges of C. So C to B, there is no edge, right? So C to B, sorry. So already C to B there is an edge, right? So C to A, there is an edge here already covered. C to B already we have constructed in the tree. C to G is 3. C to G is 3 and C to E is 4. C to E is 4, right? So among 4 edges from C, C to A is already written, C to B already considered in the tree, C to G and C to E. So this is the next one. So we need to select the least cost from this one. So which is C tends to G with a 3. So from C you can construct a G, so which doesn't form the cycle. So now, so I will consider here A with a D, with a F, B, C and G, right? So the weightages are 5, 7, 2, 15 and the edge is 3 here. Okay, edge is 3. Now we have taken one edge, that is a new vertex G. So what are the remaining edges? See, you can observe here. So A tends to B with a 14 and A tends to C with a 21, D tends to E with a 22, F tends to E with a 15 and F tends to G with 18, B tends to G with 19 and C tends to E with 4. Now the new vertex is G. Now consider from G. So G, we are having 1, 2, 3, 4 and 1, 2, 3 and 4. So first G to F. So is there any edge? There is no edge. So we have to consider G to F. Okay. So let us consider here, right? So G to F with 18. Next, G to B. G to B. There is considered. We have considered, right? G to C. So we have already constructed the tree. So G to E is 2. G to E is 2. So these are the edges. Among all these things, consider the least. So this one is the least, G to E. Now construct the tree with this one. So A, okay, A to B, F, F to B, B to C, C to G, and the last one is G to E. G to E. So the cost, let us write down the cost. It's a 5 and it is 7, it is 2, it is 15, it is 3 and again the last one is 2. Right? So this is the tree and now you can observe all the vertices has been covered. So A, B, C, D, E, F and G. Right? So all the vertices has been covered here. So we can stop here and consider the remaining vertices. So consider this A to B. So we have considered G to E with 2 and we have included the edge. Consider A to B. If you consider A to B, it forms a cycle. So we should discard. A to C. If you consider A to C edge, right? Again, it's a cycle. D to E. So D to E. Again, it forms a cycle. F to E. F to E. Again, it forms a cycle. C to G. Sorry, F to G. F to G. Again, it forms a cycle. B to G. Again, it forms a cycle. So C to E. It forms a cycle. G to F. G to F. Again, it forms a cycle. So all the edges has been covered and all the vertices has been covered here. And now you need to find the minimum cost of this particular tree. So this is the minimum cost spanning tree. So this is a minimum cost spanning tree. So you can see, so we are having all the vertices, okay, we are having all the vertices, and if the graph is having n edges, n vertices, the edges should be n minus 1. So how many vertices are there? 1, 2, 3, 4, 5, 6 and 7. 7 vertices are there. So it should have 7 minus 1, 6 edges. So 1, 2, 3, 4, 5 and 6 edges. So it satisfies the spanning tree and you can apply, you can see this is the minimum cost spanning tree for this particular graph. And here the minimum cost, I will write down here. So the minimum cost is, so how much? 5 plus 7 plus 2 plus 15 plus 3 plus 2. So how much it is? 12, 14, 29, 34. So minimum cost spanning tree, the cost of this particular spanning tree is 34. Right? So hope you understood. First you need to select any vertex and consider all the outgoing edges of that particular vertex to the new vertices and select the minimum or least weighted edge from the among all the vertices, and if that edge forms a cycle in a tree, discard that edge and consider the next least cost weighted edge, and repeat the same process until all the vertices are included in the tree. So here you can see all the vertices are included in the tree. So we have stopped the procedure and we have checked all the edges. So all the edges, if you consider any one of the edge, it forms a cycle here. So that's why we have to remove all the edges. We need to discard all the edges, right? So this is how we can find the minimum cost spanning tree by using the Prim's algorithm. Hello friends, welcome back to our channel. So today we'll see one more application of greedy method, that is Dijkstra algorithm. So someone will call it as a Dijkstra or Dijkstra. Okay, so today's topic is Dijkstra algorithm. So using greedy method. So we have seen the greedy method. What is a greedy method? So selecting the best or optimal solution from a solution set is called the greedy method. And here the Dijkstra algorithm means finding the shortest path from the source vertex to all the remaining vertex in a graph. So we know that a graph is a connected edges for all the vertices. So for that particular graph, so finding the shortest path from the source node or source vertex to all the remaining vertices. So this is also called as single source shortest path. Single source shortest path. So the main aim is to find shortest path from source vertex to all remaining vertices in a graph. So this graph can be directed or undirected graph, right? So this can be directed graph or undirected. So this algorithm will be suitable for either a directed or undirected. So before going to this one, let's have a small introduction about the graphs. So graphs will be having vertices or vertex and edges. So vertices are represented as a circle and edges are represented with a arrow marks. So this is a directed and this is a undirected. So if you are directing towards some particular vertex, that will be represented with this arrow, and if you are not directing, it will be like this arrow. And weights. So for every edge, so this is a numerical, right? For every edge which connects two vertices will be having some sort of cost, or we call it as a weight. Example, a graph A, B, C. So here we are not using this directed, right? This is an undirected graph, and it becomes directed if the graph is in this way. And here the weight of this particular edge which connects the vertex A and vertex B is represented with a numerical. So this is a numerical. So this is called as a weight. So 5 and 4. So this will be calling as a weights, and this will be calling as a edge, and this will be calling as a vertex, and we can also call it as a nodes, or we can also call it as a hops. Okay, depends upon the subject course. So vertex, node, or hops. So this is a small introduction about this graph. Now the single source shortest path will find, first we have to find out the source node. Let it be, this is a source node. For example, this is a source node. Okay, don't get confused here. I'll write source, right? Source is A. So from A, what is the shortest path for all other vertices? So A to B, A to C. Okay, so that we have to find using this single source shortest path. So where it will be used? So it will be used in order to find the shortest distance in between one place to another place. And also the same thing will be applied in a networking concept for routing a packet. So it will find the shortest path, and through that shortest path the packets will be transferred. So in many applications we will use this Dijkstra algorithm. So Dijkstra or Dijkstra algorithm, right? Whatever it may be. Now we will see what exactly happens in this single source shortest path using this Dijkstra algorithm. I'll explain with a small example so that you will be understanding, right? So I'll take it A, B, C, D. So this is an undirected. So this Dijkstra algorithm can be applicable for both the directed and undirected. I am giving the directed, undirected. So I will give the values 4, 10 and 15, right? So 5 is the weight given for this edge which connects vertex A and B. 15 weighted edge between B and C. 10 weighted edge between D, C and D. 4 weighted edge between A and D. So this is a vertex, this is an edge, this is a weight. Now we need to find, so this is a source. Let us assume this as a source. So we need to find the shortest path from A to B, A to C and A to D. Okay. See, usually A to B there is only one edge, that is a 5, and A to D there is only one edge, it's 4. What about A to C? So A to C can be done through D or through B. If A to C from B, the cost will be 5 plus 15, total 20. And if you use this path, that means through D, it will be 14. So which will be the minimal shortest path? So in order to reach C, A can travel through D, which gives the minimal cost. So here you can see we are having a multiple solutions. From these multiple solutions we are selecting the optimal solution, right? So that's why we call this as an application for a greedy method, right? Now we'll see the procedure. What happens first? Okay, so step one, find out the source node. Find source node. Find the source node. So in this example, let us assume source is A. Source is A. And step 2. Initialize the weight of or the cost of A, that means a source, is 0 and all other nodes cost is infinite. So initialize cost of source is 0 and cost of other nodes or vertices is infinite. So I'll give the weights here itself. Okay, I'll give the weights here. So I'll represent with black, small difference. So 0, and here it will be infinite, and infinite. So this is a cost. Okay, don't confuse. This is a weight and this is a cost. So from source, how much cost it takes to reach the destination. So here A is the source, and if A is the destination, the cost is 0. And if B is a destination, let it be, assume it as infinity. Right? So next, step 3. Okay, so find cost of neighbor vertices from source. So what are the neighbor vertices? So B and D. So how we can say that B and D are the neighbors, and why not the C? Because there is a connectivity between A and B and A and D. Okay, so if it is a directed graph, consider the outgoing arrow marks, not the incoming arrow marks. Outgoing arrow marks. So if it is a directed, right? Now the neighbor edge or neighbor vertex will be D, not B, because B is connected to A, but not A is not connected to B, because this is a direction, right? So in the absence of this arrow, that means this is a undirected graph. So we can say A to B and A to D, both are the neighbors. So A is having a neighbors of A to B and A to D. So find out the cost. So there is direct connection. So obviously A to B, the cost is a 5, and A to D, the cost is a 4. Right? Now change the cost. Initially, so next, step 4, change the cost on vertices, or you can see update the cost on vertices. Now you can see initially, so how we can check means the minimum of see what happens here, the cost plus weight of that particular edge, comma, existing cost. So we need to consider any one, minimum of cost plus weight and existing cost. See what happens here, A to B is a 5 and A to D is a 4. So there is a direct connectivity. So we have to go with either 5 or infinity. Okay, so here in this example you can see A to B means 0 plus 5. So here the cost is 0 plus weight is 5, comma, infinity. So among this we have to find out the minimum. This is for A to B. And similarly A to D, the minimum of 0 is the cost plus weight, 0 plus 4. 0 plus 4, what is the initial cost? Infinite. So in both arguments we need to consider the minimum. So obviously it will be 5 and obviously it will be 4. Hope you understood now. Okay, now we need to update the cost on vertices. So simply remove this one. So remove this one and update it with D, 4, right? And update this one with 5. Okay. So this is a 4 and this is a 5. Okay, 4 and 5. Now what happens? Right. Next, step 5. What we have to do? Now place the visited node in a set, visited set. For example, I mean here we will write a visited set. So write down the set. So what will be the visited node? A, because we have considered A with the shortest cost, and then okay, so and then we are updating the neighbors. So this node has been visited. So once the node is visited, we need not revisit that node. Okay, so that's why we are placing the visited node here. Now step 6, consider vertex with minimum cost. Now the cost, this is already visited, so we need not consider this one. Consider the cost of B, which is 5, C infinity, D 4. So these 3 are unvisited links, okay, unvisited vertices. So here we can have B with a 5 cost, D with a 4 cost, and C with a infinite. So among these we have to find out the minimum cost as a source. Now we can change. We can select that one. So among this we can simply say D with a cost 4, which is a minimum. Now consider this one as a visited. Okay, because this is the shortest cost among these 3. So now add it here, A and D. Okay, then step 7, update the cost on neighboring vertices. So what are the neighbors? So this has been completed. We are selecting the source as node D. Now we have selected A, and now we are selecting D. What are the neighbors for D? So one is A. There is a direct link to A, right? But A is already visited, so we need not bother about this one. We are having only one node, that is C. So D to C. So what we have to do? Update the cost based upon this one. Minimum of cost plus weight, comma existing cost. So here you can see existing cost is infinity. So what we have to do? So minimum of cost. What is the cost of D? 4 plus weight 10, comma infinity. So which one is the minimum? So obviously it will be 14. 14 is the minimum. So update this one with 14. Update this one with 14. Okay. Next, what we have to do? Repeat the same process from step 5. Okay, sorry. Step 6 and 7. Repeat the same process. Step 8. Repeat step 5 and 6. Sorry, 6 and 7. Step 6 and step 7 until all nodes becomes visited. So we have to repeat the same steps. So what is the step 6 after step 7? consider vertex with the minimum cost as a source. Now consider the source. So these are the visited, right? We need not bother about that. So these are unvisited. Now consider the same 14, C14 and B5. So C14 and B5. Which one is a smaller? So obviously this is the smallest node. Consider this as a visited and update the, what happens? Update the cost on neighboring vertices. And one point is important, that is no need to go with the visited nodes. So what are the neighbors of B, A and C? A is already visited, so we need not bother about that one. Go with the C. So what is the thing we have to do? A minimum of cost 5 plus 15 comma 14. So the cost, existing cost is 14, right? So minimum of 5 plus 15 comma 14. So what happens? This is a 20 and 14. So this is a minimum. Already the cost is minimum. So you need not change the cost. And then repeat the same thing. So add here B, right? And repeat the same thing. Consider a vertex with the minimum cost as source. Only one node is there, that with 14. So consider the same thing and go with the this one, right? So what is the order we have done? Simply go with the order. First we have seen A as a source. From that we have visited the D. From that we have visited the B. From that we have visited the C. Okay, D to C, right? D to C. And this is the minimum cost tree. Minimum cost tree. So this we call it as a tree because this is not closed. Okay, this is a open. So this we call it as a tree. So like this we have to apply the single source shortest path. Okay, so first I'll repeat once and I'll close. So in our next session we'll see one more example, right? So first consider any graph, any directed or undirected graph. So I am taking the undirected graph. So first select the source. So that will be the single source, and our aim is to find shortest path from the same source to all the remaining vertices. So here I am taking A. So we need to find out the shortest path from A to B, A to D and A to C. Now first initialize the cost of source as 0 and other vertices as infinity. So first 0 and other cost is infinity. So find out the minimum cost vertex from all the vertices. So we are having A is a minimum because it is a 0. So consider this one. And now find out the cost for all the neighbors. That also unvisited neighbors. Okay. So find the cost of, here I'll write unvisited neighbors. Unvisited neighbors. Okay. So A neighbors are B and D. So B with a cost 5 and D with a cost 4. And so A is completed because already the neighbors have been got a cost. So A will be considered as a visited. So we need not bother about A. Now we have to update the cost for each and every vertex. Now again the same process repeated. So we need to find the vertex with a minimum cost. So here 4, some here it will be 5 and it is a infinity. So 4 is the minimum cost. So we have to select the D and again repeat the same process. Find out all the unvisited neighbors and find out the cost and repeat the same until all the nodes or all the vertices have been visited. Right? So one thing, so here we are having a 2 paths in order to reach the C from A. AB, BC, AD, DC. That means we can have a multiple solutions, and from that multiple solutions we are taking a constraint as a shortest path based upon the cost of the edges. So that's why we can say this Dijkstra algorithm is an application of a greedy method. So which gives the optimal result among the several solutions, right? So hope you understood this one. Let's stop here. In our next session, I'll go with a few examples so that the complete clarity will be getting, right? So if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much. Hello friends, welcome back to our channel. So in our previous session, we have discussed about the greedy method application, that is single source shortest path. And now we'll see an example for single source shortest path. So we can also call it as Dijkstra algorithm. And example for this Dijkstra algorithm. Example, right? So before going to the example, let us recall the algorithm. Okay, so first we have to select the source node or a source vertex, and we have to give the cost of that particular vertex as 0 and cost of all other vertices with an infinity. That's the first step. Second step, among all the cost or the cost of all vertices, select the minimum cost vertex. Okay, so that will be a visited vertex, right? And from that we have to change or update the cost of neighboring nodes, unvisited neighboring vertices. And we have to repeat the same process until all the vertices becomes visited vertices. So the main aim of this particular algorithm is to find the shortest path from source to all other vertices, not from source to destination, source to all other vertices, right? Now we'll see an example. So let us take an example: A, B, C, so again I am taking undirected graph. Okay, so I'll give you some weights, random weights. I am giving some random weights. So let us take it as 8. Sorry. Okay, so this is a graph. Okay, so finally we'll get some tree. Okay, so from source, so I'll consider this one as a source. That means A is a source. So first what we have to do, we have to give the cost for every vertex. Okay, so I'll update the cost for A as 0 and all other vertices with infinity. Okay, the cost of all other vertices as infinity, right? Now we have to find out the minimum. Okay, so the first step, cost of source 0, cost of other vertices infinity. Second step, minimum of all cost. Okay, the vertex, select the vertex with minimum cost. I'll write completely. Select vertex with minimum cost. So what is the minimum cost? A, right? A. So select this one. Okay, and now we have to update the cost of adjacent. So let us select A. Okay, so let us select A. So what are the adjacents? B and F. So update the cost of B and F. So this is a direct edge. Okay, so we can update with a 5, and here it is 7. Okay, 5 and 7. All remaining are infinity. And mark this one as a visited node. So A is visited now, because from A we have find out all the cost of adjacent vertices. Okay, so we only two neighbors. So we found the cost of these two neighbors, B and F. Now we need to find the cost of, so the second step, we have to repeat the second step. What is the second step? Select the vertex with minimum cost. So I'll update here visited. So A is visited, and next upon all these things 5, 7, infinity, infinity, infinity. So among this one, which one is the highest? Sorry, minimum? 5. So select B. Select B. Now find out the neighbors. Okay, what are the neighbors? One is A, another one is F, another one is C. And you can observe A is already visited. You can see A is already visited, so you need not bother about A. So we need to find the cost of neighbors, unvisited neighbors, F and C. Okay, F and C. So what is the C? Update. So 5 is a cost. Here source is A, right? So the name itself indicates it's a single source shortest path. So we need to find out the shortest path from the same source. From A to B it is 5, and from B to C 5 plus 6 it will be 11. So the path from A to C via B will be the 11, and we have updated it. Now we need to find out the F. Okay, F. So from B to F it will be 5 plus 8. Okay, so don't forget to count the actual cost plus the weight, because here the source is fixed. That means we are finding the path from A itself. So here B to F means A to B and F. So this implies A to B, B to F, A to C, sorry, A to B, B to C. Okay, so A is visited and we are finding the next minimum path. So B to C it was 11, and B to F, what happens? 5 plus 8. Okay, so for this one it will be 5 plus 8, which gives 13. So we need to find the existing cost and the calculated cost, and we need to select the minimum among that one. So here already F is visited with a 7. Okay, there is the shortest path from A, it is 7, and now through B it will be 13. See, A to F is 7, and A to B and to F it will be 13. So among this one, which will be the shortest path? Obviously this will be the shortest path. So we need to select the minimum. Okay, minimum. So we need not update this one. We need not update this one. So we have already done with the neighbors of B. We have already done with the neighbors of B. So we can add this B to the visited set. So this node is visited. Now repeat the same process. Select the vertex with the minimum cost. So here vertex means unvisited. So here unvisited are F, C, D, E. Among all these one, which is the shortest, minimum cost? Here 7, it is 11, infinity. So F is the shortest one, minimum cost. So we can select F now. And now find out the adjacent neighbors of F. F, A, B, E. And you can see A and B are in the visited. So simply you can ignore. Okay, we need not revisit that particular vertices. Okay, only there is a path from F to E. So the cost is 3. But here this implies what is this one? A to F and F to E. So what is a to F? It is 7. The cost plus 3, 10. In order to reach from A to E, the cost will be 10. So this is a 7 and this is 3, which gives 10. Right? So update this cost 10. Okay. So any other neighboring edges? No. So obviously we can add this to F. Okay. And this is the visited. F is visited now. Now repeat the same process. Again, from the unvisited nodes or unvisited vertices, select the minimum. So which one is having the minimum? E with 10, C with 11 and D with infinity. Obviously E is the minimum. So E, and find out all the adjacent or the edges, neighboring edges. So E to F, E to C, E to D. Okay, E to F, E to C, E to D. Not this implies A to F, F to E. So we can write it here. A to F, F to E, and now E to F or E to C or E to D. So here any vertex in the visited, yes, F is already visited. So you need not worry about this one, F. So we have to find out the cost for E to C and E to D. So E to C, see, E to C. E to C means, see, A to F, F to E, E to C. Similarly, A to F, F to E, E to D. So what is the cost here? So A to F is 7, 7 plus 3, 10. So here we got a 10. So simply we can say 10 plus C, 10. See, E to C it is 10. So total 20. Already the cost of C from A is 11. That means the path or the distance required for A to reach C is 11 through B. And the path from A to C through F and E becomes 20. So which one will be the lowest? So obviously 11 will be the lowest. So we can discard. So we have to select the minimum. Okay. Now coming to this one, E to D. E to D. So already 10 is the cost to reach up to E, and to D it will be 12. So update this with 12. 12. So this will be 10 plus 2, it will be 12. And 12 and existing is infinity. So 12 and infinity, the minimum will be 12. So we are updating here. And what happens? Any other edges? No. So obviously we can select E as a visited. E as a visited. And here it will be E. Again, we are having a 2 more unvisited vertices. That is C and D. Select the minimum cost vertex. So among this C and D, C is the minimum. C is the minimum. So what we have to do? So we need to select C. In order to get C, we are using A to B, B to C. So what are the adjacents? C to B, C to E, C to D. And this comes from B and it comes from E. This implies. So we are just having the path from C to B, C to E and C to D. Select, verify whether any vertex are in the visited. So B is visited, so you need not worry about this. E is also visited, you need not worry about this. So we are having only one edge, that is from C to D. So that implies A to B, B to C, C to D. So up to C it is 11 plus C to D it is 4. So which is 15. So from A to reach D, the cost is 15 through C. But through E, it becomes 12. So among this 12 and 15, which is the lowest? 12. So we can discard. So Any other edges? No. So simply you can add it to visited. So you can add it to the visited. And now repeat the same process. Consider all the unvisited vertex, and from that unvisited vertex find out the vertex with the minimum cost. So we are having only one unvisited, right? Only one unvisited. So only one, and rest of all are visited. So obviously this will be visited with a 12. So this will also be added in the visited set. So this is the procedure to find out the minimum cost for each and every vertex from the source vertex. So first source is A. So B, C, D, E, F are the different vertices. So we are finding the shortest path to reach all other vertices from the source vertex. Okay, so what is the shortest path? Let us take A to B, that is directly it is a 5, and A to F, it is directly a 7. So what about C? So A to B, B to C, it is 11. Next, E, A to F, F to E, it becomes 10. Next, A to F, F to E, E to D, it is 12. So this is the cost from A to B, A to F, A to C, A to E, and A to D. So you can apply here. First step, A, so it is a visited, and after that B. Next it becomes a B. Next it is F. Next visited is E. Next visited is C. Next visited is D through E. So this becomes a tree. This is not a graph, because we know that graph is a connected, right? So closed graph, closed loop. So here it is not connected, right? This is a tree, minimum cost tree from the single source. So this is the source. This one will be the source. Okay, so hope you understood this one. So the problem is finding the source node and finding the shortest path from source to all other vertex. Okay, so here I am not talking about the destination. So we are not considering the destination as D and finding the cost to reach the destination. So here the question is finding the shortest path from source to all other nodes. Okay, right? So this is the procedure, and what is the time complexity of this one? What is the time complexity? So one point is finding all the vertices. Okay, so considering all the vertices from A, all the edges. So what we are doing here is, so we are selecting A and all vertices, edges B and F. Next we are getting B and all vertices A, C and F, and we are finding the C with B, E, D and E, and D with C and E, and E is having some C, F and D, and similarly F is having A, B, E. So we are selecting each and every vertex and finding the edges, the cost of all incoming or outgoing edges. Okay, so that implies in order to iterate each and every vertex, it will be n minus 1, and again we have to repeat all the edges. So the maximum edges we can get is n minus 1, right? If n vertices are there, it can have n minus 1, right? So n minus 1 edges. So it will be n square. So the time complexity is order of n square. Order of n square for this particular Dijkstra. And this is an example application of greedy method, which is used to solve the optimization problems. So here you can observe, in order to reach C, it can go with A, B and C, also A, F, E and C. And in order to reach F, it can directly go with a direct edge, or it can reach till A, B and F through B, right? So for this kind of problem, we are having a multiple solutions. So here, in order to reach F, what we are doing? In order to reach F, A to F is one path, A to B to F is another path. So we are having a multiple paths, and again we can have a multiple A to B, B to C, C to E and E to F. So that's also one path. So that means for finding the cost or reaching this one, so we are getting a lot of paths, multiple paths. But what we are selecting the path with minimum cost. So that means the shortest path. So that kind of problems we call it as a greedy method, and this particular algorithm is implemented or solved by using this greedy method, selecting the optimal solution from a solution set, right? So let's stop here. Hope you understood this complete procedure. So if you want to know the procedure step by step, so visit the previous video. In the previous video, I have explained the complete step by step with a simple example, and here in today's session we have seen one example along with this finding the final complexity, type complexity, right? So let's stop here. If you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you are really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.